Hi, everybody. Welcome to the next topic in our statistics course, known as standardized scores, or what we're going to refer to as z-scores. In this chapter, we're going to be learning about how we can take any raw score on a test or an assessment and convert it into a standardized score. Now, there are several advantages of doing this, and we'll talk about what those are. But just to kind of get going here, we're going to be completely focusing on z-scores, standardized scores. And this whole process is going to allow us to locate scores in standardized distributions. Okay, so when we talk about a z-score, we're talking about turning a raw data value into a z-score or a standardized score. Now, why would we do this? Well, there's two main purposes. When we convert a raw data point into a standardized score, we're able to tell the exact location of the original score within the entire distribution of people that took the test. Okay, so it allows us to locate where that particular score falls relative to the entire distribution. Now, even more importantly, z-scores or standardized scores allow us to directly compare results or scores that come from two completely different distributions with their own mean and their own standard deviation. If we take those two raw scores and we put them on the same platform or the same scale, we can see which score is more or less competitive than the other. So, what is the purpose of z-scores or standardized scores? Well, they not only allow us to locate where the score falls relative to the rest of the group, but the transformation of raw data into z-scores allows us to directly compare data from two distributions that wouldn't otherwise be directly comparable. Okay, so let's just look at an example of this. Okay, over here in figure A, okay, John scores a 76 on his chemistry test. Okay, and on the chemistry test, the mean score was a 70, and the standard deviation was 3 points. Okay, as a result, a score of 76 is well above average. Okay, that puts John almost in the second standard deviation, okay, 2 standard deviations above the mean, with his score of a 76. In other words, because the average was 70 and the standard deviation was relatively small, 3 points, a 76 is 2 brackets above the mean and is a very competitive score. Okay, he did very well on this exam relative to the rest of the class. Now let's look over here at figure B. This is the Spanish exam. Okay, the average on the exam was a 70, but look at how much bigger the standard deviation is. Okay, there was much more spread in terms of how people performed on this Spanish exam. The standard deviation is 12 points. This means that John's score of a 76 in Spanish is nowhere near as competitive as it was on the chemistry test. Okay, a 76 is not even 1 full standard deviation above the mean. Okay, so this is just an example of how the standard deviation is really going to impact how competitive or non-competitive a score is. Now, if we wanted to directly compare these scores, we can do something even easier. We can just convert them to z-scores, and that will allow us to directly compare both of these exam results on one single distribution, known as the z-distribution. Okay, so let's talk a little bit about z-scores. Okay, calculating them is relatively simple. We'll talk about that in a few moments. But when we compute a z-score, we're going to get 2 pieces of information. Okay, the z-score is going to be positive or negative. Positive z-scores indicate that that result is above the average. Okay, negative z-scores mean that that score falls below the average. The number itself tells us how many standard deviation units or brackets that score lies above or below the mean. For instance, if I calculated a z-score of positive 2.0, that would mean that that original score is 2 full standard deviations above the mean. Okay, so go ahead and take a moment. Think about what a z-score of positive 3.0 would be telling you. Okay, that would be a result that's 3 full standard deviation brackets above the mean. Alternatively, a z-score of negative 3.0 is telling you that that score is located 3 standard deviations below the mean. To go back to our example here, okay, on the chemistry test, John's 76, if we were to calculate a z-score, would be equivalent to 2.0. Okay, it's 2 full standard deviation brackets. Whoops, sorry about that. It's 2 full standard deviation brackets above the mean. Okay, 3 and 3, 6 points above the mean. Okay, the 76 is equivalent to a z of 2.0. Okay, so here is our z distribution. Okay, the mean of the z distribution is 0 and the standard deviation is 1. Okay, those are characteristics of the z curve. The mean is 0 and the standard deviation is 1. Okay, let's go ahead and do a practice question. A z-score of positive 1.0 indicates a position in the distribution that is what? Is it above the mean by 1 point? Above the mean by a distance equal to 1 standard deviation? C, below the mean by 1 point? Or D, below the mean by a distance equal to 1 standard deviation? Well, the positive value indicates that it's above the mean, right? And the number is telling us by how many standard deviation brackets. Okay, so the answer here is B. A z-score of positive 1.0 tells us that that score is 1 full standard deviation bracket above the mean. Okay, so it's important to be able to interpret these z-scores and know what they're telling you. Okay, some true-false. A negative z-score always indicates a location below the mean. Okay, absolutely. Anytime we have a negative z-score, that means it's below the mean. Let's do the second one. A score close to the mean has a z-score close to 1.0. Okay, this requires remembering the characteristics of the z distribution. A score close to the mean is going to have a z-score close to 0. Remember, the mean of the z distribution is 0 and the standard deviation is 1. Here is our equation for computing a z-score. Okay, in order to take any raw data point and turn it into a z-score, we simply take that score and subtract the mean from that value, and then we divide by the standard deviation. Okay, so we're getting a deviation score up top. How different is that raw value from the population mean? And we divide by the standard deviation. This formula can be found on the formula sheet for z-scores. Alternatively, you may wish to write it down right now so that you can do some practice problems as we go through the rest of this lecture. Okay, here's a practice question. A distribution of scores has a mean of 100 and the standard deviation of 10. What z-score corresponds to a score of 130 in this distribution? What you're going to do is take the 130 and use the z-score formula to create a z-score. Okay, go ahead and do that. This should be fairly simple. Okay, there's our formula, right? Z equals 130 minus 100 divided by 10, we should get a z-score of 3.0. That means that 130 is 3 full standard deviations above the mean of 100. Okay, there's the math there for anybody who is having a little bit of trouble. This tells us that a score of 130 is highly competitive. Anything that's 2 standard deviations or higher above the mean, or even below the mean, are extremely rare. Those are really extreme scores. Okay, so here's a slide I want you to spend some time on. And I want you to go through on a piece of paper. And first of all, up top, I want you to find z-scores for all of the raw data points listed here. Okay, a score of 65, 48, 70, and 53. Okay, here are your population parameters. Okay, the mean is 60 and the standard deviation is 9. Okay, so go ahead and use that information to compute z-scores for each one of these values. Once you're done with that, I want you to work backwards. If we know the raw value, okay, we can create z-scores, but we can also go back from z-scores to the raw value. Okay, here we have a z-score of negative 1.0 and a z-score of 2.0. I want you to take these values and turn them into their original scores. Now, you may be able to do this intuitively by looking at the standard deviation, okay, of 9 points, but for those of you who want a simple, shortcut, error-free solution, go ahead and use the formula I've provided down here. Okay, to go back to the raw x value, it's simply the mean of the population plus the z-score times the standard deviation. Okay, take a few moments to work on these questions. Okay, go ahead and pause the video. I'm sure some of you are still definitely working. I'm going to go ahead and continue, okay, with the rest of this lecture video. Okay, these are the answers for those practice questions. Okay, so check your z-scores and make sure they line up with the results on this slide. Okay, an x-score of 65 is equal to a 0.56 z-score. That means the 65 is a little bit over half a standard deviation above the mean. And here are your other answers. If you've had trouble with this, go ahead and bring your questions to class, and we'll address them in class. Okay, and here are our results. If we find the original score that equates to a z-score of negative 1.0, that means that it's 1 standard deviation below the mean. Well, if the score, if we know the standard deviation is 9, we can just say, okay, it must be 60 minus 9, that's 51. Same thing over here. A z-score of 2.0 means that that value is 2 standard deviations above the mean. Well, the mean is 60. 2 standard deviations is 9 plus 9, 18. 60 plus 18 is 78. Okay, so go ahead, go through the math again if you had any problems. Bring them to class. We'll address them in person. But you should be able to take raw data points and turn them into z-scores. And alternatively, you should be able to take a z-score and, knowing the population mean and standard deviation, convert it back to a raw score. Okay, here's another question. For a population with a mean of 50 and a standard deviation of 10, what is the x value corresponding to a z-score of 0.4? Okay, I suggest using the formula for this one. You can also do it intuitively by doing 0.4 times 10 and adding that to the mean. Okay, here our answer ends up being, right, 54. Right, if we do 0.4 times 10, that's equal to 4 points. We add that to 50, we end up with a 54. Okay, true or false? If the population mean is 40 and 50 corresponds to a z-score of 0.20, then the standard deviation must equal 10 points. Okay, the standard deviation must be 5 points. Okay, if z equals 0.2, then 2 standard deviations is 10. So 1 standard deviation is equal to 5. Okay, this is 2 standard deviations above the mean. That means 1 standard deviation must be half of 10, 5 points. If the standard deviation equals 20, a score above the mean by 10 points will have a z-score of 1.0. True or false? Okay, the z-score is going to be 0.5. If the standard deviation is 20, then z equals 10 over 20, that's 0.5. Okay, 10 is only half of 20, so that's a z-score of 0.5, not 1.0. Okay, here's another question. In a population with a mean of 65, a score of x equals 59 corresponds to z equals negative 2.0. What is the standard deviation of the population? Okay, if the population has a mean of 65 and a score of 59, 6 points below 65, corresponds to a z-score of negative 2.0, what is the standard deviation of the population? Okay, it has to be 3 points. Oops. Right, 2 standard deviations below 65, 59, that's 6 points, divide by 2, and you end up getting 3.0. In a population with a standard deviation of 6, a score of 33 corresponds to 1.5. What is the mean for the population? Okay, if a score of 33 corresponds to 1.5 standard deviations above, right, we just subtract 3 and then 6 and then 6. What do we end up getting? Okay, and for those of you looking at my notes, you'll see the mean must be 24C. Okay, all of the solutions are found in the PowerPoint slides here that are also uploaded separately to D2L so that you can look at without the video. Okay, so you should be able to take information like this, knowing a raw score, knowing the standard deviation, knowing what z-scores are telling us, and be able to figure these kinds of pieces of information out. If you are struggling with this, I want to encourage you to definitely read the chapter in your textbook. Okay, reading is not optional in this course. Students that are going to get great grades and earn A's in the course are going to be reading the textbook diligently. If you're still having trouble after doing that and then rewatching this video, bring your questions to class as always. Now we're going to spend some time talking about standardizing an entire distribution. Okay, every x value in a data set or on a test can be transformed into a z-score. Now we've already talked about the characteristics of a z-score transformation. Importantly, when you transform all of the scores on a survey or on some kind of test into a z distribution, you're not going to affect the shape of the data. Okay, the shape is going to stay the same as the original distribution, which means that if you had skewed data or abnormal data beforehand, a z-score transformation is not going to change the shape or fix that for you. By definition, the mean of the z-score distribution is always 0, and a standard deviation is always equal to 1.0. A z-score distribution is one example of a standardized distribution. There are other standardized distributions out there. The SAT test has its own standardized distribution. The ACT test has its own standardized distribution. And IQ tests have their own standardized distributions with a mean of 100 and a standard deviation of 15. Okay, any score can be converted into a standardized score, and all scores can be converted to create a standardized distribution. Okay, so when we're transforming scores, okay, to z-scores, all we're really doing is relabeling the axis and putting them on a new platform where they can be directly compared. Okay, here's some kind of test or measurement where the mean is 100 and the standard deviation is 10. If we go through and convert all of the scores to z-scores, we now put them on a platform where the mean is 0 and one standard deviation is equal to 1. Okay, you're basically making the axes just simpler. Okay, the mean is 0 and the standard deviation is equal to 1. Okay, that's a good way to think about this whole z-score transformation. We're just relabeling the axes. Okay, a score of 100 in the original distribution is now equal to a 0, and a standard deviation bracket, instead of being 10 points up here, is now equal to 1 point. Okay, all z-scores are directly comparable to each other. One of the biggest benefits of z-scores is that we can take results from different tests and from completely different distributions, turn them into z-scores, and then make direct comparisons of those scores. Okay, now that we've put them on the same z-score platform, because they've been converted to the same scale, we can see where scores fall relative to other scores, even though they're coming from different distributions. Okay, put simply, they allow us to compare scores from different tests that would have otherwise been very difficult to directly compare. Okay, here's a great example. I'm sure many of you remember taking tests to get into college. Now, some of you will remember the SAT test, and some of us may have also taken the ACT test. Okay, these are both college admissions tests, and some people will take both to see which one they do better on. Okay, which test should they submit to colleges in order to increase their chance of getting accepted? Now, let's say you took the ACT and you got a 26 on the test, okay? And on the SAT, you got a 620. Now, it's really hard to directly compare these results. They're on different scaling platforms. By looking at this, I have no idea whether I should pay to have my ACT score sent to the U of A, or should I have my SAT score sent over to the U of A? I'm not quite sure by looking at these scores which one is more competitive. One solution for this is to take both of these test results, turn them into z-scores, and then I'll be able to figure out which one is more competitive. Okay, I'll basically put them on the same comparative platform, the Z platform. Okay, well, here we have the parameters for the ACT. Okay, the mean is 18, and the standard deviation is 6. Okay, for the SAT, the mean is 500, and the standard deviation is 100. So go ahead, I want you to practice this right now. I want you to take the population parameters for the ACT and the SAT and convert both of these scores, 26 and 620, into z-scores. Okay, convert those values into z-scores and tell me which one is more competitive, which one is the better score. Okay, go ahead and spend a few moments doing that. I'm going to pause the lecture video for a moment, and I encourage you to do so as well. Okay, let's go ahead and see how we solve this question. Well, let's calculate z-scores for the two tests. There is our z-score formula. Okay, so we're going to create a z-score for the ACT result of 26, and we are going to compute a z-score for the SAT result of, was it 500? Sorry, 620. 620. Okay, which one is better? 26 on the ACT or 620 on the SAT? Well, 26 on the ACT minus 18, which is the average, divided by 6, which is the standard deviation, we get a z-score of 1.33. Okay, over 1.25 standard deviations above average. Not bad. What about the SAT? Well, a 620 minus 500, which is the population average, over 100, the standard deviation, gives us a z-score of 1.20, just a little bit shy of 1.25 standard deviations above the mean. These results are pretty comparable. Okay, however, I would submit the ACT test. Okay, this z-score of 1.33 just edges out the SAT result. Okay, this was a slightly better performance. Okay, the better score is the ACT score of 26. When standardized, the relative location of this score is further above its mean than the SAT score of 620 is above its own mean. Okay, that's the point of z-scores. They allow us to take these two incomparable results, put them on the same platform, and make direct comparisons. Okay, if you have any distribution with a known mean and a known standard deviation, you can go ahead and compute a z-score. The process of standardization is used widely. Okay, the SAT has its own standardized distribution where the mean is 500 and the standard deviation is 100. That means anybody all over the world can take the SAT and we can see where you fall relative to the rest of the population. You might remember that terminology. You're in the 80th percentile. You're in the 40th percentile. That's telling you where you fall compared to everybody else. If you're in the 40th percentile, that means you did better than 40% of test takers. If you're in the 90th percentile, you did really well. You beat out 90% of the competition. Okay, IQ tests have a mean of 100 and a standard deviation of 15 points. That's the standardized IQ scale. You can take an IQ test, the WACE, the Stanford-Binet, any kind of standardized IQ test, and we can convert the score to the standardized IQ distribution to see where you fall compared to the rest of the population. When we standardize a distribution, there's simply two steps. We have to transform all of the original raw scores into z-scores. Okay, and then we take the z-scores and transform them to new x values so that the specific mean and standard deviation are attained. Okay, let's look at that visually. Okay, here are some original scores on some kind of test. Okay, the mean happened to be 57 and the standard deviation was 14. Well, we can convert all of these to z-scores. Okay, 1 and 2, 1 standard deviation below the mean, 2 standard deviations below the mean. And what we can do is then standardize the distribution and create the kind of mean and standard deviation gap that we want. Okay, in this case, the mean is 50 and a standard deviation is equal to 10. In short, if you have original data, you can always transform it into a z distribution and then even use the z distribution to transform it into your own standardized distribution where the specific mean and standard deviation you want to use are on the scale. Okay, here's a question. A score of 59 comes from a distribution with a mean of 63 and a standard deviation of 8. Okay, notice that 59 is 4 points below 63, so that's half a standard deviation below the mean. 4 is half of 8. This distribution is standardized to a new distribution where the mean is 50 and the standard deviation is 10. What is the value of the new score? Okay, well, what's half of 10? It must be 55. Oh, sorry, 45. We're talking about a value that's below, let me see that. Score is 59. Right, because it's below the mean. Okay, so it ends up being 5 points below the mean, 45. Okay, populations are the most common context for computing z-scores. Usually we want to see where somebody falls relative to the rest of the entire population. However, we can also compute z-scores for samples. Okay, it's the same exact process. We just want to be clear up front that we're talking about sample data and that we're using samples when we factor in our mean and our standard deviation to get those z-scores. So to kind of wrap this up, I want to look ahead a little bit to inferential statistics. Okay, z-scores are great. They allow us to locate a specific score in the distribution, and they also allow us to directly compare scores that come from two different tests that would have otherwise been incomparable. However, z-scores do something else for us too. They allow us to define what's noticeably different in research studies. Remember, in most of our research, the interpretation of the results depend on determining whether or not a sample is noticeably different from the population. Okay, if I take a sample of people with clinical depression and I give them some kind of cognitive behavioral therapy, well, I hope after 6 weeks, if my treatment was effective, that they are now noticeably different in their symptoms from the untreated clinically depressed population. One technique we have for defining noticeably different involves z-scores. Okay, so let's just go through this example. Let's imagine that this is a population of individuals diagnosed with clinical depression. Now, I take a sample of 1,000 people in Tucson who have met criteria for a clinical depression diagnosis, and I subject them to a 12-week-long cognitive behavioral therapy, okay, that I have good confidence is going to reduce symptoms of depression. 12 weeks later, I measure their symptoms, right? What I can do is I can compute a z-score to see how different the treated sample is from that original population, okay? Are they now much different in terms of where they fall on the curve in terms of their symptoms? Okay, so we hope that the z-score for the treated sample is significantly lower in this case, right? Their symptoms have gone down compared with the untreated population. Okay, we can even look at the z-score for the sample before it was treated and compare it to after it was treated. Z-scores give us an indication of how much the sample has shifted in one direction or another on the normal curve, in this case looking at symptoms, due to our treatment or our intervention. Okay, just for shorthand, z-scores of positive 2.0 and negative 2.0 are where we draw the line for noticeably different. If a sample obtains a z-score of 2.0 or a negative 2.0, they are now much different from the original population. We consider them to be statistically different from the population they are drawn from. Okay, positive 2.0 and negative 2.0. Okay, let's go ahead and do this question. Last week, Andy had exams in chemistry and in Spanish. On the chem exam, the mean was 30 with a standard deviation of 5. Andy scored a 45. Okay, above the mean on that one. On the Spanish exam, the mean was 60 and the standard deviation was 6. Andy had a 65. For which class should Andy expect the better grade? Okay, which score was more competitive? Go ahead and take those results, turn them into z-scores, and then make a decision about which result is more competitive. Okay, the chemistry exam is more competitive. Okay, the mean was 30, right? The standard deviation is 5. If you take 45 and turn it into a z-score, that's equivalent to 3 full standard deviation brackets above the mean. Extremely high-performing result. Okay, in Spanish, right, the mean is 60, the standard deviation is 6. A 65 isn't even 1 full standard deviation above the mean. Okay, his chemistry exam was way better. He did way better compared to the rest of the class than he did on the Spanish exam. Okay, true or false? Transforming an entire distribution of scores into z-scores will not change the original shape of the data. Okay, that's true. Z-score transformations are not a fix for abnormally shaped data. You will get the same exact shape of the data. Number 2, if a sample of 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. Okay, think about that one carefully. Okay, that's false. Okay, the number of z-scores above or below the mean is going to be exactly the same as it was in the original distribution. If you have skewed data, negative or positive, okay, you might get more scores above or below the mean. Here's the bell curve, the standard normal curve, okay, and you can see different z-scores, okay, z-score of 0, 1, 2, 3, okay, and also going out to the negative side. And this curve here is just showing you the percentage of people that will fall in which portions of the curve. Okay, so about nearly 70% of the population is going to fall within 1 standard deviation above or below the mean. Most people are average and are falling in these average areas. And we have fewer cases, fewer subjects scoring in these extreme tails. Okay, so when you know the standard deviation, when you know a z-score, you can also have a pretty good idea of the percentage of cases that fall in that bracket or that group of brackets. Okay, what's the percent of people that typically fall there? Okay, so that's going to go ahead and wrap up the intro coverage of z-scores or standardized scores. Okay, this is chapter 5. You should be working through the chapter 5 practice problems in MindTap and bringing any questions you have to class. We're also going to take this one step further. We're going to be introducing probability shortly, and you'll see that once you know a z-score, you can look up the probability of obtaining an individual with that z-score from the population. What's the chance of selecting certain people with certain z-scores? Okay, we're going to be using our first statistical reference table, known as the normal unit table. I will post a copy of that on D2L. I'll also bring some hard copies into class. But you should be kind of finalizing chapter 5 and reading chapter 6 right now. We're combining these chapters because they really are very complementary to each other. Okay, I will see you in the next video.